Okay, so for number 10, we have a function f here, x squared over x minus 2 squared, and we need to answer a lot of different information about that. So part A asks us to find the locations of the horizontal and vertical asymptotes. So when you have a rational function like this, one that looks like a fraction, your horizontal and vertical asymptotes should be relatively simple to determine. So your vertical asymptotes are whatever makes the denominator 0 after any simplification can be done. So if you notice here, this is already simplified as much as possible. Like there's no way that we could cancel anything out here, so this is already set for us, and the vertical asymptote then would be whatever makes the denominator equal 0. So in this case, our denominator is x minus 2 squared, so the only thing that would make that 0 is x equals 2. So we have a vertical asymptote at x equals 2. To find the horizontal asymptotes, when we have a rational function, what we do is look at the degree, compare the degree of the numerator and denominator, and use our rules for there. So if you notice here, the degree of the numerator is 2, the degree of the denominator is also 2. So when the degrees are equal, the horizontal asymptote is just going to be the ratio of the coefficients on those leading degree terms. So the leading coefficient here is 1, and if we were to expand this, the coefficient on the x squared there would also be 1. So we just get 1 over 1. So we get a horizontal asymptote of y equals 1. So we have one horizontal asymptote and one vertical asymptote. Part B asks us for the critical numbers, increasing, decreasing, concave up, and concave down. All right, so we had a lot of information to figure out for part B, but the main thing is we have to take the derivative to do that. So we're going to start by taking the derivative. And to do the derivative of this, x squared over x minus 2 squared, we're just going to use the quotient rule. So we do the derivative of the top times the bottom minus the derivative of the bottom. So in this case, we don't really have to use chain rule because the derivative of the inside is 1 anyway. So we can just treat that as a standard x, essentially. Derivative of the bottom times the top. And that's all over the bottom squared. So you can see here, every term has an x minus 2. So we can cancel, or sorry, this should be to the fourth down here, because it's bottom squared. We cancel one copy of x minus 2 from everything. And let's factor what's remaining in the numerator. So what's remaining in the numerator is 2x times x minus 2 minus 2x squared. So note that we can factor out 2x. If we factor out 2x, what's remaining here is x minus 2, because that's the only thing we took out. And here, if we factor out 2x, we still have an x, so we'd say minus x. So you can see here that in our remaining parentheses, after we factored out the 2x, we get x's to cancel out, x minus x. And then we just have negative 2 times 2x. So in most simple form, this is negative 4x over x minus 2 cubed. So that's our derivative. So now we can answer a few of these questions. We need to find the critical numbers and the intervals where it's increasing and decreasing. So remember that the critical numbers are whatever make this derivative 0 or undefined. Now we have a fraction, so both of those are possible. But recall that you can only have a critical number if it's in the domain of the function. So x equals 2, for example, though it makes this derivative undefined, that's not a critical number because x equals 2 is not in our domain. So you couldn't plug in 2 to the function, so that's not a critical number. What is a critical number, though, is x equals 0, because that makes our derivative 0. And that is perfectly in the domain of the function. So we have one critical number, x equals 0. So now let's find the intervals of increase and decrease. So if we're going to use the first derivative test to find intervals of increase and decrease, what you need to put on the number line are critical numbers and vertical asymptotes. So we have a critical number at 0. We also have a vertical asymptote at 2. And I'll denote that on my number line by drawing a dotted line. So even though a vertical asymptote is not a critical number, you still have to put it on your number line because it could be increasing on one side and decreasing on the other, or vice versa. You don't know. It still could affect increasing and decreasing. So now we just use our first derivative test. So we're going to be plugging numbers in here, here, and here, and we're just going to check them in the derivative and see if they're positive or negative. So here, less than 0, we just plug in any negative number. Our numerator would be positive because we're doing minus 4 times a negative. Our denominator would be negative because we have a negative number to the third power. So we get positive over negative, which is negative. Plug in something in between 0 and 2, like 1. Our numerator is negative. Our denominator is still negative. So now we get positive. And finally, if we plug in something bigger than 2, our denominator is now positive. Numerator is still negative. So that's minus over here. So there's our intervals of increase and decrease. So writing those in interval notation, our increasing interval is 0 to 2. And our decreasing intervals are negative infinity to 0 and 2 to infinity. So those are our intervals of increase and decrease for this function. We also need to find the intervals of concavity, and that requires that we do the second derivative. So let's start here and do the second derivative. Again, we need to do quotient rule. So derivative of the top is just negative 4 times the bottom, x minus 2 cubed, minus the derivative of the bottom times the top. Well, the top's, let me write this a little bit better so you guys can see it all in one line. So this is negative 4x times, negative 4 derivative of the top times the x minus 2 cubed minus the derivative of the bottom times the top. So we're going to get negative 4x, and we're going to get the derivative of the bottom, which is going to be 3x minus 2 squared. That's all over the bottom squared. So our bottom was x minus 2 to the third. So if we square that, we get x minus 2 to the sixth. And now we can do some simplification. So everything has lots of x minus 2's. And in fact, we can cancel out 2 copies of x minus 2 from everything, because this copy of x minus 2 over here is squared. So we can get rid of that. And this would be lowered to power 1. This would be lowered to power 4. So we canceled out an x minus 2 squared out of everything. And what else can we factor? We can see here that this has a 4, this has a 4. And in fact, this one's negative, so let's just factor out negative 4. So if we factor out negative 4 in the numerator, what we'd be left with is in the first term, we still have x minus 2, because that had 1 copy left there. In the second term, we have minus, and so we cancel out the negative 4. We still have a 3, and we still have an x. All right, I'm going to continue my work over here. So now let's do a little bit more simplification here. X minus 3x becomes negative 2x. So we get minus 4. So this would become negative 2 minus 2x all over x minus 2 to the fourth. And then we can do one more step of simplification because these both have a negative 2. So we can factor that out as well. And we'd get 8. X plus 1 all over x minus 2 to the fourth. Okay, so this is our second derivative as simple as possible. Let's figure out how we can assess concavity. Obviously, 2 is a vertical asymptote. That's not a critical number, but it still has to go on our number line. Our numerator could be 0 if x is equal to -1. So when we draw our number line for our second derivative, we again just have 2 things to put on there, this time -1 and still 2, which is a vertical asymptote. So to check concavity, again, we're just going to test points in each interval, and we're going to draw it on here, or pick numbers and plug them back into this. So if we choose something less than -1, the top would be negative. The denominator here is always positive because it's raised to the 4th power, so we don't have to keep checking that. So this is going to be minus. Something in between -1 and 2, like 0. Numerator is positive, denominator is positive, that's positive. And something bigger than 2, numerator is positive, denominator is positive. So notice we have this line up here for the first derivative. We have this line here for the second derivative. And now we can do the last part, which is to sketch a graph. So if we were to try to graph this, the first and most important thing to put on it is that we know there's a vertical asymptote at x equals 2. So I've put a vertical asymptote at x equals 2. We know that it has a it has a min at 0. Because it goes from decreasing to increasing, and that's a critical number. We could figure out exactly what that point is by plugging 0 back into the function, and if you see, that's pretty easy. If you plug in 0 here for x, you get 0. So this graph goes through the origin, and that is in fact a min. Remember that we said we also had a horizontal asymptote of y equals 1. So we have that horizontal asymptote as well. So what's going to happen here is this is a graph that's actually going to cross its horizontal asymptote, and we can figure out how that happens. Let me write this up here. We know our horizontal asymptote is going to be x equals, or y equals 1. So if we set our function x squared over x minus 2 squared equal to 1 and solve for x, we could figure that out. How you would do this is you would multiply this over, expand that out, and then simplify algebraically. I'm going to not do all those steps in the interest of time here in graphing this function, but if you notice, what happens if you plug in x equals 1? Your numerator would be 1. Your denominator would be -1 squared, which is 1, and that is in fact equal to 1. So x equals 1 is the place where this crosses our horizontal asymptote right here on the graph. So remember, if you know that there's a horizontal asymptote, that's a y value. So if you set your function equal to that and you get an answer, there is such an x that happens, that means you cross your horizontal asymptote at that point. All right, so we're about ready to finish graphing this now. So let's start from the left and continue on. So up until 0, this graph is decreasing, and it's also concave down. It has to intersect this point 0, 0, because that's the min. But this is the only place where it crosses the horizontal asymptote. So that means the only way that this could look is something like this. And notice, I might not have drawn that so clearly. At x equals -1, we have an inflection point, and it has to switch to concave up. If you think about it, that should make sense because you kind of have to switch to concave up in order to hit the minimum value. So it looks something like this. And we have a minimum right here at 0. So the rest of the time, this is concave up. So we're only doing concave up from here on out. It's increasing as it approaches the vertical asymptote, so the only way that could look is like that. And from the rest of the past two, it's decreasing, concave up, can't cross these asymptotes. The only way that that could possibly look is like that. That's decreasing, concave up, won't touch the asymptotes. So what I've just drawn here is an approximate graph of f of x.
The Teaching Center, UF's Learning Resource Center.